Myself Punyamurthy from Department of Chemistry, IIT Guwahati. I welcome you all to IIT PAL program. In today's class, we will study about aromatic hydrocarbons. Aromatic hydrocarbons that contain at least one aromatic ring, and they are also called arenes. And for examples, so this is benzene, naphthalene, anthracene, cyclopentadienyl anion, cycloheptatrial cation. These all are aromatic compounds, and they also can be derivatives. For example, toluene or methylbenzene. This is simple benzene, and it has substituent. One of the hydrogen has been replaced, and all these compounds are aromatic compounds. If you look at all these compounds, they have only carbon and hydrogen atom, therefore, they are called aromatic hydrocarbons. And they can be broadly divided into two groups: the compound that contain benzene and its derivatives, benzene, naphthalene, anthracene, and this one. If you look at all these compounds have 6-membered ring, and that they are fused 2 6-membered rings and 3 6-membered rings. Here it has a one of the hydrogen has been replaced by methyl group. These compounds are called benzenoids. These compounds are called that compound hydrocarbons that contain benzene and the derivatives, they are called benzenoids. The other compounds, which are their aromatic, double bond is missing, aromatic, but they are not, they do not have benzene ring. These are called non-benzenoid hydrocarbon, aromatic compounds. They are called non-benzenoids. So, aromatic hydrocarbons can be classified two groups, that they contain the benzene and derivatives, or the other they are aromatic compounds, but they are 5-membered, 6-membered or 7-membered hydrocarbons. Now, let us look at the structure of benzene as taking example. So, benzene is a planar molecule. As you can see here, it has 6 carbon atoms, 6 hydrogen atoms, and they have equal bond length. And if you look at the structure, so the bond length is 1.39 Armstrong. So, all carbon CC bond has same bond length, and which is 1.39 Armstrong, which is, if you compare with carbon carbon single bond, which is 1.54 Armstrong. So, the carbon carbon bond length in benzene is smaller than carbon carbon single bond of alkane. On the other hand, if you compare with carbon carbon double bond alkene, is 1.34 Armstrong. Is slightly longer than alkene carbon carbon double bond, and slightly shorter than carbon carbon single bond. The bond length of benzene is in between carbon carbon single bond and carbon carbon double bond. So, let me draw the molecular orbital structure of benzene. If you look at it, each carbon has 3 sp2 hybridized orbital, and 2 of this orbital, this sp2 hybridized orbital, 2 of this orbital overlap with neighboring carbon atoms. For example, in this case, this sp2 hybridized orbital overlap with this sp2 orbital of this carbon to make carbon carbon sigma bond. Similarly, overlapping of these two sp2 hybridized orbital leads to the formation of this carbon carbon sigma bond. In addition to that, each carbon has another sp2 hybridized orbital. Basically, it has 3 sp2 hybridized orbital, 1 p orbital with 1 electron, and overlapping of this sp2 hybridized orbital with the s orbital of hydrogen generates sigma bond, CH sigma bond. So, this involvement of this sp2 hydrogen orbital in the sigma bond formation makes the benzene ring planar molecule, and the bond angle between these two carbon carbon or carbon hydrogen bond is 120 degree. They have uniform length, whether carbon carbon bond length or CH bond, they have identical bond length, and the bond angle between this carbon hydrogen and carbon carbon bond is 120 degree. And this involvement, as I mentioned just now, involvement of this sp2 hydrogen orbital in the sigma bond formation makes benzene as a planar molecule. This is the sigma bond formation benzene. As you can see here, each carbon has 3 sp2 hybridized orbital which overlap with the 2 of this orbital with 2 carbon atoms, 1 hydrogen atom makes 3 sigma bonds, carbon carbon and carbon hydrogen, 2 carbon carbon and 1 carbon hydrogen sigma bonds. Now, in addition to that, each carbon has 1 p orbital with 1 electron, and let me draw you have the 6 p orbitals, and this orbital parallel to each other, and each has 1 p electron, 1 pi electron. Each p orbital has 1 electron and they overlap. Side on approach to generate and as you can see here, above and below the plane, this is your benzene ring, and above the below the plane you have the bimolecular orbital. So, this is a p orbital, the 6 p orbital they overlap together to form a pi molecular orbital which has 6 electrons, they are delocalized, and above 50% of this pi molecular orbital above the benzene ring and 50% of the molecular orbital below the benzene ring makes more stable. This is the molecular orbital structure of benzene, as you can see here, and this involves the sp2 hybridized orbital, the sigma bond formation, and in addition to that there is also p orbital which overlap and they generate a bimolecular orbital, and above and below the plane, as you can see, there is a bi cloud and makes the delocalization of this bi electrons makes benzene ring more stable, about 36 kilocalories mole, more stable comparing to the simple 1,3,5 hexadriene. When you have 3 carbon carbon double bond, if you compare the stability of this one, this is more stable, this because of the delocalization of the bi electrons, and as you can see here there is a ring current above and below the plane of the benzene ring. This makes the benzene is more stable. Next, resonance and stability. just we have seen the structure of benzene, and if you look at it, it looks single bond, double bond, single bond, double bond, single bond, but that is not right. So, benzene is basically say a hybrid of resonance structures. So, these are the two main resonance structure. This is a hybrid of what is resonance structures, different structures, but the atoms are the identical position. Those are called resonance structures, and benzene is basically a hybrid of resonance structures. Can be written like this, or this means the electron density is equally distributed in all the carbon atoms, and that leads to extra stability of benzene and make the carbon carbon bond length and CH bond length uniform in the benzene ring. So, basically and is a hybrid of resonance structures that makes benzene is more stable. The another term you have to remember is aromaticity. So, a compound to be aromatic, and they have to be planar and cyclic. A compound to be aromatic hydrocarbon, it should be, or there are also aromatic compounds, they have heteroatoms. A compound to be aromatic, they should be planar and cyclic. Then they should have delocalized pi electrons, that is very important. Delocalized pi electrons. And third, they should have 4n plus 2 pi electrons, where n equal to 0, 1, 2, 3, etc. should be integer. So, a compound to be aromatic, they should be a planar and cyclic, they should have a delocalized pi electrons, and they should have 4n plus 2 pi electrons. The n can be 0, 1, 2, 3. So, if the compounds satisfy the following then they can be aromatic. For examples, let us take benzene. Just we have seen benzene as a planar and just planar molecule. It is a cyclic, as you can see here, and so it satisfies the first one, planar and cyclic. Delocalized pi electrons, it has a delocalized pi electrons, each carbon has one p orbital and it has one electron, all 6 electrons delocalized. Then 4n plus 2 pi electrons, you should have 4n plus 2 electrons, pi electrons, and in this case you have 2 to 6 pi electrons, you have 6 pi electrons, and 4n plus 2 equal to 6 electrons, and 4n equal to 4, n equal to 1. So, in the benzene n equal to 1, this is aromatic. Now, let us take the another molecule. So, naphthalene. Say bicyclic aromatic hydrocarbon, and if you look at this molecule, this also planar and this is a monocyclic, that is a bicyclic. Two benzene ring fused together, and anyway cyclic compound, that also cyclic and planar molecule, and they also have, it also has delocalized pi electrons, as you can see here, and these are completely highly conjugated. All carbons, you have the double bond, single bond, double bond is written like this. It's a conjugated system, delocalized pi electrons, and then let us count. It has 10 pi electrons. 4 n plus 2 equal to 10, 4 n equal to 8, n equal to 2. So, it satisfies all this whatever mentioned here. It is a planar and cyclic, it has delocalized pi electrons, it has 4 n plus 2 pi electrons, therefore, this is also aromatic. Now, let us, these are examples for benzenoids as we have seen the beginning. Now, let us look at non-benzenoid compounds. Let us take cyclopentadienyl anion. The beginning we have seen as aromatic. This is a cyclopentadiene. See the sp2 carbon, sp2 carbon, in addition to that you have the sp3 hybridized carbon in between. So, when you treat with the base, the base can remove this proton, it's acidic. So, you can generate cyclopentadienyl anion. Here what happens to this p orbital, whatever this p orbital has the lone pair of the electron in this. So, this is cyclopentadienyl anion, and if you see the orbital structure of this molecule, the p orbitals delocalized in this case. Now, whatever the lone pair of electrons is in the p orbital. In other words, the lone pair is involved in the delocalization of this the 5-membered ring, and make this molecule is planar and is cyclic. Already the molecule is cyclic, and it this lone pair under delocalized with the p orbital of this sp2 hybridized carbon, and make the delocalized orbital. You can see here this has 2 electrons, this has 1 electron, 1 electron and 1 electron. This is a bi bond, this orbital overlap of this orbital gives a bi bond, and the lone pair of electron, the p orbital overlaps, it makes delocalized pi electrons, right. So, if you now see whether it has 6 electrons or not, 4 n plus 2 pi electrons, and you can see here it has 6 electrons, 4 are coming from the double bond, 2 comes from the lone pair, 6 electrons you have, n equal to 1. Therefore, this compound is aromatic. And it is not a 6 benzene, but this compound is aromatic, and this is called non-benzenoid compound. The other example is tryptophan cation or cycloheptatrienyl cation. So, this also is not a 6 membered ring like benzene, but 7 membered ring. It has 6 pi electrons. In addition to that, you have a carbon where a vacant p orbital is there. The p orbital in this case is vacant, does not have any electron, and this vacant p orbital overlaps with this p orbitals that contain electron, pi electrons, and makes delocalized molecular orbital. See, this vacant p orbital overlaps with this p orbital that contain electron and makes a delocalized molecular orbital that makes it aromatic. And this also cyclic, planar, and as soon as you form this one, then if you count the number of electrons, it has 6 electrons, therefore, this compound also aromatic. Now, let us look at the nomenclature and isomerism. For IUPAC nomenclature, you have to place the name of the substituent prefix to benzene. For examples, let us look at these molecules, and here the methyl group is present in the benzene, therefore, is called methyl benzene. This is called chlorobenzene. This is called aminobenzene. So, when you have more than one substituent, for example, let us take these two molecules. Here 2 bromine atoms are bonded with this benzene, here 1 chlorine and 1 bromine atoms. So, for nomenclature, IUPAC nomenclature, and we have to when you have more than one substituent, then we have to introduce a numbering, then we have to place before the as prefix before the benzene, and for this case you have no problem, both are bromine atoms. So, we can call at 1,2-dibromobenzene. Here, now there are 2 different substituents are present, and we have to follow the alphabetical order when we numbering, and bromo comes first, therefore 1, then C, chloro, C comes second, therefore this is called 1 bromo, 2 chloro, benzene. So, when the molecule contains 2 different substituents, we have to start numbering from alphabetically, and in this case B comes first, therefore, I have numbered as 1 and then C comes, therefore, I have numbered as 2. Then we have to place the substituent name before prefix to benzene, and then we can get 1 bromo 2 chlorobenzene. Now, let us look at the isomerism of substituted benzene. Let us take dibromobenzene. There are 3 possibilities there in the case of 1,2-dibromobenzene. This is just we have seen as 1,2-dibromobenzene. This is 1,3-dibromobenzene. This is so, they have same molecular formula, but different structures, and in this case the bromine atoms present at carbon 1 and 2, therefore, is called 1,2-dibromobenzene, and is present and at carbon atom 1 and 3, 1,3-dibromobenzene and 1 and 4, 1,4-dibromobenzene. These are called isomers, or this is called regioisomers. And similarly, we can see for tribromobenzene. So, if you look at these molecules, they are also isomers, but they have different structures. This is called, let us compare these 3 molecules. They also have same molecular formula, but different structures. These are also called regioisomers. Preparation of benzenoids, industrial process, and first we let us look at it, the preparation of benzene and its derivatives from petroleum. When we subject alkanes like that contains C6 to C8 carbon atoms, for example, hexane, platinum, which is supported alumina around 500 to 600 degrees Celsius and 10 to 15 atmosphere pressure. They can undergo cyclization to give cyclohexane. The cyclohexane can be further converted into benzene, hydrogen. So, in petroleum industries, whatever the alkanes are produced that contain C6 to C8 carbon atoms can be readily converted into benzene in large scale by reacting with platinum which is supported on alumina at high temperature and high pressure to give cyclohexane. The cyclohexane can be further converted into benzene by dehydrogenation. On the other hand, instead of hexane, and if you have heptane, under the same reaction conditions can be converted into methyl cyclohexane that can be further transformed into methyl benzene. And in case of octane, okay, this is one of the large scale process used to make benzene and its derivatives from petroleum by cyclization followed by dehydrogenation process. The other large scale process is the distillation of coal tar Coal tar is a mixture of aromatic hydrocarbons, benzene, naphthalene, anthracene and so on. When you distill at different temperature, you produce light oil. Light oil contains benzene and xylene and so on. When you distill coal tar and you get the light oil, that when you wash with acid to remove the base, then base to remove the acid, then final distillation can produce benzene and toluene and xylene and so on. This is one of the another process used to make benzene, and industrial process is distillation of coal tar. In addition to that, there are also methods available to make benzene and its derivatives in the laboratory scale. The first method is treatment of benzoic or substituted benzene carboxylic acid with the soda lime. When you react benzoic acid with soda lime, and carboxylic acid will be converted into benzene and sodium carbonate. This process used in the laboratory. The other process is reaction of alkynes. For example, 3 molecule of ethane when you combine together, when we pass through red iron hot, to give benzene. This 3 molecule can combine together under these reaction conditions to give benzene. This another method used to make benzene. The third approach is if phenol is available, when we treat phenol with zinc dust, and it can undergo reaction to give benzene and zinc oxide. So, these are the three common methods are used to make benzene in the laboratory. For industrial process, just we have seen from petroleum industries, and we can produce a lot of C6 to C8 alkanes that can be readily reacted with the platinum catalyst, which is supported alumina at high temperature pressure. They can be converted into the corresponding benzene derivatives. And the another approach industry uses to make benzene is distillation of coal tar at different temperatures at below 200 degrees Celsius, and that is called light oil that can be distilled out from coal tar, that can be further treated with acid followed by base, then water, and we will end up with a mixture of benzene and methyl benzene and so on, that can be further distilled to get pure benzene and methyl benzene compounds. Now, let us look at the physical properties of benzene. Physical properties. So, aromatic hydrocarbons benzene and their derivatives are non-polar compound, so they are usually solid or liquids. They are liquids and solids. They are well soluble in organic solvent. And insoluble in water. Aromatic compounds exhibit strong odor, and the vapors of aromatic hydrocarbons are toxic in nature. In summary, so in this class we have seen part of aromatic hydrocarbons. First, we have seen the structure and bonding of benzene. Then we have seen the resonance and the stability of benzene, then aromaticity, the nomenclature and isomerism, and preparation of benzene. At the end of the lecture, we have seen the physical properties of benzene. With this, I conclude. The next lecture, we will see about the reactivity of benzene.